So this is a screencast about, sorry about that, the part of the course for mechanics a lot of people had trouble with, mostly, that was rotation. So chapters 15 and 16 out of your 5 steps to a 5 deal with that. I'm going to do a cursory trot through chapter 15 because they said that universal gravitation is not on this exam. I'm a little, I question that though. And the reason I question it is because energy is still on the exam, and things like gravitational potential energy, where does that fall? So at any rate, I'm going to go through a little bit of this, but definitely chapter 16, which has rotation a lot more. So overall, that's a formula for centripetal acceleration. Centripetal force is just mv squared over r. It can be caused by lots of things. It could be caused by magnetic force, friction, gravitation force. So that's Newton's law of universal gravitation. This is gravitational potential energy. That was weird. Wow. So I've seen that normally as UG is equal to negative of these things. Anytime you have two things that attract each other, you have negative potential energy. So a positive and negative charge. The formula for that is U sub E, because it's electric potential energy, is equal to K, Q1 times Q2 over R. Why is that one not negative? Well, because the charges attract when one of these two is negative. If both are negative or both are positive, they repel and you'd have positive electric potential energy. But here you do need to put the negative in front of that. So bound systems are characterized by having negative total mechanical energy. Hey, that page is left blank. So this stuff you should know. You should know how to convert back and forth between linear and angular measurements. So V, omega, A, alpha, X, and theta. You may want to write that on your formula sheet. Normally you wouldn't be able to do that. But those types of things where you would think of, say, God, listen. Let's do a different font. I'm not a fan of Helvetica. Let's go back to Times New Roman. Okay. Ooh, I don't. That's no Traditilio. Okay, so something like that. We could say that X is equal to theta times R. So radians times the radius. Could also say that now velocity is equal to omega. Looks like a wonky W. I can't do a wonky W. And that's in radians per second. And then finally, angular regular acceleration alpha times r. So that's radians per second squared. And so then you could go and rearrange those, obviously. So omega is equal to V divided by R and things like that. So, yeah. Yeah, that's a good point. Don't label a force on something as a centripetal force, although you will not be asked to make free body diagrams. You may be asked to interpret them. So again, you would never label something as a centripetal force. You would label it as something causing that, like a gravitational force, or who knows what that could be, what else it could be. Okay. Oh, my wireless mouse has got dust on it. I better not screw around with it, otherwise I'm going to screw it up. Okay, so, oh, this is a good example. Something going on a vertical circular path when there is gravity versus when there's not gravity. We did something like this in class. So although the motion is tangential, the top of the path you would have a net force down at the bottom of the path. You have a net force up, but the tension would not be the same at the top and bottom. Gravitational force would be the same, and that's always directed down. But since your centripetal force, if you were going a constant speed, would be the same, that if we were, that's not what I want, if we were up at the top of the path here, you could say that this would be, the net force would still be the same. So it would be that, like say a centripetal force caused by the tension and mg. Here, the centripetal force would be up. So this tension would have to be longer than the centripetal force. It has to overcome gravity. So your tension is most at the bottom, least at the top. You have, pardon me, allergies. A critical velocity, which is the least possible speed this could go and stay on a circular path when the centripetal acceleration is 9.8 meters per second squared. And if that's true, that means your tension up here would be 0, and your tension down here would be equal to 2 mg. Car on a curve is another really good one. So friction is pointing inward if you're on a flat surface. If you're on an angled surface, so something like that, friction could either point up or down depending on how fast you're going. So if you're going really, really fast, you might imagine that you would want to continue a straight line and go up to the top of the oval or the car's circular path. If it's not, you might want to go, might want to slide down if you're going very slow. And so therefore friction could point in either direction. If you have an object on a regular incline not going in a circle, friction would normally point up the incline. So we've talked about that. Kepler's laws, I guarantee you're not going to have to know. Energy of closed orbits might be important. So you may want to read through this. I don't think you're going to have a calculation on this, but like this is something that a little bit odd. So that was a pretty short chapter. So now when we go to this rotational motion, that's the biggie, right? So something like this, you know these general equations. These are the calculus versions of them. So big ideas here. Moment of inertia is equal to some sort of coefficient times mr squared. For a point particle, that's a 1. For it's a continuous body, they say something like this. But again, this depends on how far out the mass is from the center. I guess they did these conversions in here. So rotational kinetic energy, torque, is equal to moment of inertia times alpha. That is Newton's second law for rotation, so that's equivalent to F net equals m times a. And angular momentum. Angular momentum for a point source is simply mvr. If you have something that's a body that's not a point source, you would probably not use that. So let's get into it and see what they have to say in here. Again, these are all analogs of your linear motion equations. I could definitely see one of the longer free response questions being something where it asks you to compare something linearly and rotationally. So I think that's going to be kind of important. This is the part of the course where if you're calculating things, you would need to do things in radians. However, because you're really not going to have to write equations down, from what I understand, I don't know if that's going to be that necessary or not. You do want to understand conceptually that a radian is just part of a circle. It's like a degree or a piece of pie or something like that. It is just a piece of or a part of a circle. This part's really important. So this the rotational object inertia of an object is its equivalent to mass. It depends on how much mass the object has. It depends on the shape of the object, and it depends on the radius of the object. So if we think about things, a sphere has a coefficient here of 0.4 mr squared. A hoop where all the mass is on the outside, 100% of the radius, mr squared. A solid disk that's of uniform density, 0.5 mr squared. So they go through and talk about how to calculate those. You may want to look at the page in your textbook about where they end up showing you the formulas for moments of inertia for different shapes. It basically deals with where the average mass location is located. I wouldn't say the center of mass, but the average mass location. Because the center of mass for a hoop or a disk or a sphere is still, if it's uniform density, in the center. But oftentimes I've seen things like these rolling races where things go down a hill. So because those three objects would have the same torque if they had the same radius, but they have different moments of inertia, you would end up having the sphere win and then the hoop would lose because it has the highest moment of inertia. Interestingly enough, if there's minimal friction, an object sliding down would beat them all. The way you can think about that is if you have something going down a hill, go back up here to these formulas. If it's rolling, if it starts at the top of the hill, it has gravitational potential energy, mgh. If it's at the bottom of the hill and it's just sliding, it just has 1/2 mv squared. But if it's at the bottom and it's rolling, it's still moving linearly, 1/2 mv squared, but it also is rotating and has some of the energy as kinetic rotational energy, 1/2 I omega squared. So essentially what we've got is we've got the total potential energy at the top now split among two types of kinetic energy at the bottom. So since it's split, it'll be moving slower. And I don't know who's sending me all these messages. So we'll go down here. So this is a really good type of problem. If this pulley has mass, then it would affect things. First of all, if the pulley has mass or if the rope has mass, then the tension in this rope would not be the same as the tension in this rope. If the pulley is massless and the string is massless, the tension would be the same. So if this is a solid disc and the string is on the outside of it and the disc mass is 0.5 kilograms, essentially a solid disc has a coefficient of 0.5 mr squared. So this acts like a mass of 0.25 kilograms. So I've gone through several examples of how to solve those things. Here they're going through an example of solving tension, by the way. I like this from your understanding standpoint. But recognize that all objects, this one, and the outside surface of this pulley would be accelerating at the same rate, same number of meters per second squared. And then you can use the equations which were shown earlier, these ones, to relate meters per second squared to radians per second squared. And that's how you can figure out some things about that pulley. They talk about what I was just talking about there with the things rolling down the hill. Wow, it's like I should have looked at this stuff earlier. Again, kind of neat there. They derive the speed of this. If you had a solid sphere, which is 0.4 mr squared, your final velocity would be in terms of that. If you had a solid disk, which is 1/2 mr squared, then this would be essentially 1/2 mv squared plus 1/4 mv squared. So this would be 1.33 instead of 10/7, I believe. Angular momentum is actually pretty important. So it is always, always, always conserved. Remember, that's Henry Brandstetter. Okay, so what we may end up doing is, like I said, this is always conserved, just like linear momentum is always conserved in all collisions. Energy may not be. Mechanical energy may not be. So energy can be converted into heat and other things. So for a point particle, this could be rewritten as mvr. Well, why is that? Well, I, for a point particle, is mr squared. Omega is equal to v divided by r. So v divided by r times mr squared gives me mvr. Kind of nice to know that. So if you have an object in a non-circular orbit, its angular momentum is conserved at all spots. So because it's closer here, it would be going faster. Farther away here, going slower. You could also think of that in terms of conservation of energy. Most gravitational potential energy here, least speed, that would work out as well. But I do think that understanding about conservation of angular momentum is important. There's not much else in this chapter. I would look at some of these. I think these are useful. I would definitely look at the tests we had before. I think I gave you some practice-free response with rotational things in January. I'd look at those and make sure you do the ones that we're giving today. So that's all I've got on that. Hopefully you'll have some questions for this on Tuesday in class. And thanks for being part of class. I really mean that. So